Hi, good morning. Good morning. Okay, get to work. Topic 6.5, energy of phase changes. Share screen now. Hope you're doing all right. Should have seen this last year. I know my students did. And what I have on my screen is pulled from your notes, copied and pasted here. I don't have the actual task value or know where it is in your notes, so I do apologize for that. I'll get back to that. Let's kind of use that as maybe a practice problem. Let's look at heat. Whoa, dear goodness gracious. See how big that was? That's too small. All right. All right, heating, cooling curves and phase changes. All right, oops, let's get that out of there. Okay, let's look at a heating curve. A heating curve is actually a graph, and a cooling curve is actually a graph. They are opposite of each other. One over here, we're going to look at the temperature changes over time as we kind of heat up a substance. So let's go like this. Let's assume that this was for water. So down here, let's go ahead and be in the negatives. Let's say we're at like negative 50. Make this degrees Celsius, okay? This is not going to be to scale, mind you. Thanks. Not going to worry about that, all right? Sorry, I just put that there. We're going to go like this. Let me think. All right, so if this was for liquid or for water, not liquid water, but H2O, right? At negative 50 degrees, water is a solid, right? So I want you to think about it like this. I've got my solid, all right? I am adding heat, all right? Time is passing and I'm heating it up. How do I know that? Because the temperature is rising. I'm heating it up, I'm heating it up, I'm heating up my solids. You've got a piece of ice that's getting warmer, but it's still ice. Well, once that temperature reaches 0 degrees Celsius, what's going to happen? Well, that ice is going to start to melt, okay? The ice is going to start to melt. So right here, I have a solid forming or turning into a liquid, right? I think that's kind of spelled wrong. It looks weird. I have a solid turning into a liquid. Please note that during this phase change of the solid turning into the liquid, the temperature is constant. It is not changing. All right, so you're adding heat, but the temperature has stopped changing. It's stopped going up. The molecules are not gaining any more average kinetic energy as you continue to add this heat. What is happening is you are overcoming intermolecular forces. That is what that extra energy is working on. It is not working on increasing the temperature, increasing the kinetic energy of the particles. It is working on overcoming intermolecular forces. So right here, mind you, as we add heat, we are causing more vibrations and more energetic motion. Right here, as we add heat, that is not what's happening, as opposed, rather, we are overcoming intermolecular forces. At this part, we are not overcoming them. We are beginning to overcome them, right? We are beginning to overcome those intermolecular forces. We're not completely overcoming them. I'm not going to write that. Okay, and then at once all of that solid, all of those intermolecular forces have been overcome, we will then see our water start to, our liquid water start to increase in temp. Okay. Okay. And that's going to happen, right? The energetics of the particles are getting greater and greater and greater. And at some point, those particles are going to have enough energy to exit the system and no longer be a liquid, but start turning into a gas. All right. And we know that for water, that's going to happen typically right around 100 degrees Celsius. And we will have, let's put that up there. I think we'll put that about right there, 100 degrees Celsius. And at that point, our temperature stops increasing. We do not increase the movement of the particles. Rather, we completely overcome intermolecular forces, such that this right here would probably require more energy here than this would here. Okay, so we would have it would take a longer amount of time because we have to overcome more forces of attraction. It kind of would make sense, right? So the liquid heats up, and once the liquid starts to boil, it no longer increases in temperature because that extra heat energy is overcoming intermolecular forces of attraction completely. All right, so I think that this would require more energy than this would, right? If that doesn't make sense, ask about that. Once all of your intermolecular forces have been overcome and there are no more liquid, there's no liquid present, you just have a gas, and that gas is going to continue to heat up rather quickly. And that, guys, is what we call a heating curve. Now, we could cool this substance down, right? That's a heating curve. We could cool this substance down, and it would be a cooling curve. So we would start, let's say we start at 150 degrees Celsius. We're going to cool the gas down, right? Once that gas gets to a particular temperature, let's say this is for H2O, those molecules will start to form attractive relationships with each other, right? And we'll see that gas begin to condense and turn into a liquid. You can see that in your head, right? Once all of the gas particles have formed intermolecular attractions with other gas particles, and we now have a liquid, that liquid can begin to cool down. And we know that it will continue to cool down until it gets to a certain temperature to where those particles can begin to come together in a very organized way and start to solidify. And that begins to happen for water at 0 degrees Celsius. And at that point, they will all find a very organized structure, if you will. And our liquid, the intermolecular forces will increase until all liquid particles are no longer liquid particles because they've all become closer. They've formed strong polar attractions with other water molecules. And then that solid just continues to get colder and colder and colder as those attractive forces as it condenses and condenses and gets colder, and they slow down, right? So here's your time. So that is your cooling curve. Okay. Now, you simply, it's not always for water, but what you know is that wherever you have the flat portion is your phase change, right? And what you know is during the phase change, there's no temp change. That's right, during phase change, no temp change, constant temp, right? What do we say? The heat is going towards overcoming those intermolecular forces. All right, so what we need to do, guys, is talk about the energy of this and do some calculations here. So let's look at some of these numbers. The specific heat capacity of ice is 2.05. So let me go like this, and you do the same. I'm going to draw another curve. I'm just going to draw my generic curve. Okay. We know that this is time and this is temp. Okay. And that's messy. Okay. And notice that they're talking about ice. So once again, it's water. So what we often do, and let's give this a -20 this time. Let's give this a 0. Let's give this a 100 again. Now, if we need to calculate the energy required to take a sample of solid H2O and increase that temperature to any temperature, maybe 50 degrees Celsius, maybe to its melting point, 0 degrees Celsius. We need to be able to calculate that, okay? And we need to be able to relate what we are doing here with any other substance, right? It's not always water. It could be aluminum, right? It could be anything, any substance. So let's get going. I'm sorry. Right here, where we see our temperature go up, the heat required to change the mass of the substance would be equal to the specific heat of the substance in the solid form multiplied by the change in temperature. This right here is the specific heat of the substance, and for water, the solid form is ice. So we see that for water, this value, if this is water, is 2.05 joules per gram. Now look, they wrote Kelvin. You have heard me say joules per gram degrees Celsius. But we've already talked about how Celsius and Kelvin, this is the change in temp, right? If you see right here, it's the change in temp. And we know that Celsius and Kelvin have the same scale. So the change is the same. We've already talked about that. So these can be used interchangeably, guys, okay? It doesn't matter that they're different because they're the same. So I'll just go with what's given to me here and not worry about the Celsius down here. Even though these are Celsiuses over here, it doesn't matter because it's the change in temperature, okay? Now, over here, my temperature is changing. So I will need a change in temp in my equation. So I will say the Q and of the liquid, right, is equal to the mass of the liquid, the specific heat of the liquid, and the change in temp of the liquid. And for water, this is 4.18. Now right here, it says 4.18. I usually write 4.184. It's just, and I usually write degrees Celsius, but I'm gonna write Kelvins to prove that it just doesn't matter. And here the temperature changing of the gas. So the heat gained by the gas is equal to the mass of the gas, the specific heat of the gas, and whatever that change in temp actually is. And for H2O, steam is 2.08. They don't call it, never mind, 2.08 joules per gram Kelvin. Okay. Now notice these are Q values. You are solving for Qs. Let me go ahead and change my color here. You're solving for Q, that is heat, the heat, the heat. If you are heating up, you will have a positive Q, right? If you are cooling down, you will have a negative Q because you will have heat removed, all right? It's important that you just realize that. Signs are very important here. Heat gained, right? Positives and negatives are very important in these units about heat. Okay, now what do we do during our phase changes when the temperature does not change? Therefore, we cannot plug in a 0 for the change in temp, because if we do, we will get an answer that tells us that 0 heat has been gained, and that is not true. We've been adding heat, and the heat's been overcoming the intermolecular forces. So in order to solve for Q, oh gosh, what do we do? Oh, yeah, I do Q. Now I'm looking at my screen. I see that this is a solid to liquid line. So Q equals my delta H fusion times my number of moles. Okay? So what is delta H fusion? It is, so fuse, first of all, is our solid to liquid, liquid to solid process fusion. The delta H is the heat required to cause the process. And when I say heat, maybe I should say exchange, because we could be adding it or removing it, freezing or melting. The units for delta H fusion are in kilojoules per mole. So when we multiply these values, the units here are in kilojoules. Okay? Now, the next phase change also has something like that. Sorry, my words are horrible today. It's Saturday morning. It's about 7:30 right now. Okay. This is the energy required to cause this process is equal to the delta H VAP. That is for vaporization. All right. That is the liquid to gas or gas to liquid process. All right. And it's also multiplied by moles of the substance. It is the energy required, the heat exchange required to cause the process, right? And it is also in kilojoules per mole. So once again, and we'll be finished here soon. When I, please look at this equation, when I solve for this equation, when I multiply my kilojoules per mole times moles, I get kilojoules, all right? Once again, this is going to be in kilojoules. However, on my other equations, let me get a different color here. Let's look at this equation. When I multiply my mass, which is grams, times my specific heat, which is joules per grams Kelvin or degrees Celsius, times my change in temp, which is Kelvin or degrees Celsius, I'm left with joules. And sometimes I have to add these values together. So I have to make sure that I account for the fact that the phase changes are going to give me kilojoules, and the heat in when we're increasing temperatures of solids, liquids, or gases, it's going to give me joules. I circled the wrong thing. Okay, it's going to give me joules here, joules and kilojoules. Let's look at an example problem. I'm going to make up my own example problem. I would do A, and just running out of room. How much energy is released when 1 mole, 18 grams of water, at 20 degrees Celsius is frozen and then cooled to a temperature of -2 degrees Celsius? All right, so go ahead and get started. Pause, maybe. All right, let me read that question again. I've got 1 mole, 20 degrees. Oops, sorry. All right. Well, if I'm at 20 degrees Celsius and I need to cool, what's going to happen is if you look at my cooling curve here, oh, good, worked out well. I'm just going to do it down here, right? If I'm at 20 degrees Celsius, then I'm, about right here. What I need to do is I need to get from 20 to where that phase change is going to occur. So I need to get from 20 degrees Celsius to 0 degrees Celsius, right? That'll get me from here to here. And I do that using Q equals MC delta T, okay? Up above, it said we had 1 mole of water, which is equivalent to 18.02 grams of water, right? So in order to take the liquid water that's at 20 degrees and get it to its freezing point, I would say Q equals my mass of water, 18.02 grams, my specific heat of water, 4.184 joules per gram. I'm just going to use degrees Celsius because that's what I have here, right? It's easier on the brain, Final minus initial. Okay, so that's 0.0 minus 20.0. Units cancel. Calculator. Get 18.02 times 4.184 times negative 20. Make sure I didn't make a mistake typing it in. Q equals negative 15 point, looking at my sig figs here. I'm not going to worry about it. 15.1 joules. So that's how much needs to be removed, right? So what I'm going to write is, right, so negative, or hold on, I'm sorry, apologize. 15.1 joules removed, right? Now, once we get to the liquid, where we start to go from a liquid to a solid, we do not have our, what we're going to do is go from 0 degrees Celsius as a liquid to 0 degrees Celsius, as a solid, right? So we'll say Q equals delta H. Now we're going from liquid to solid, so that would be the fusion, right? And we'll multiply that by the number of moles. So Q equals, well, what is the value of that? I don't recall, I haven't seen it yet this year. Molar heat of fusion for water, that's right, 6.02 kilojoules per mole. That'll be given to you guys. 6.02 kilojoules per mole. And in our problem, recall, we had just 1 mole of water. So we see that that's 6.02 kilojoules of heat removed just to get it from the liquid to the solid. Now recall in the problem, we needed to get to -2. So now what we're going to need to do is go from 0 degrees Celsius as the solid, right? Let's look at our chart. Now we need to take this down just, let's change the color, just a little bit so that we can get here over to like -2. Right? So what we have going on is we're going from 0 to -2.0 degrees Celsius, okay? And it's still a solid, right? And that would be the change in temperature, QMC delta T. Q equals the mass, that was the 18.02 grams. C, the specific heat of water as a solid up here was 2.05 joules per gram. We're in Celsius. And our final -2 minus our initial 0 is -2. And that's 18.02 times O2 times 2.5. Q equals -73.9 joules, or 73.9 joules of heat removed. Okay, so the question was, what is the energy? So what we've got here is each step. We've got the 15.1 joules plus the second step, which was 6.02 kilojoules. So we'll have to change that. Let's go like this, 15.1 joules plus 6.02 kilojoules. And we know that every 1 kilojoule is 1,000 joules. So we can just put that right there. Plus, right here, the 73.9 joules. Let's see. So I'm going to go ahead and do the 6.02 times 1,000, and then plus 73.9 equals plus 15.1 equals, and I get 6.109 times 10 to the 3 joules. Excuse me. Maybe 6.11 times 10 to the 3rd joules. Or maybe you put that into kilojoules and you got 6.11 kilojoules. All right, now let's finish this because there's another question. Consider only the energy released in the phase change. Okay, all that energy was released. What would be the temperature rise observed in a heat bath made of gold with a mass of 0.502 kilograms? The heat capacity of gold is 0.129 joules per gram Kelvin. Okay, I'm going to do that problem right here, but I need to remember this number. What was it? 6.11 kilojoules. Okay, 6.11 kilojoules released. Now let's look at the problem. What would be, whoa. Only, Miss Murphy just got tricked. Only the phase change. The phase change, students, was this right here. The heat released in that phase change was 6.02 kilojoules. So that is the value we're talking about here. Notice most of the heat was released in that phase change, wasn't it? 6.02 kilojoules. Okay, sorry. You can pause and move on. What would be the temperature rise observed in a heat bath made of gold with a mass of? So this is 6020, right? We're going to Q equals MC delta T. I know they're talking about MC delta T, guys, because the temperature, they're asking for how much will it rise? So I'm going to get the change in the temperature, right? So I know Q is going to be 6020 joules. I know my mass is going to be my 0.502 kilograms. Let's make that grams, 0.502 kilograms. And we know that every 1 kilogram is 1,000 grams. So that's going to be 502 grams, 502 grams. We know that the specific heat of gold is 0.129, 0.129 joules per gram Kelvin. And they are asking us how much the temperature will rise. So whatever we get here will be how much it's going to go up. So let's just do 6020 divided by parentheses 502 times 0.129. I've got here I'm going to stick with 3 sig figs. 93.0. So the change in temp equals 93.0 degrees Celsius or 93.0 kelvins. It's going to go up by that much. That's a messy screen, but it's not too bad, is it? Okay. I do want to look at one more thing. No, just remind me. Remind me, we'll talk about it in class, is, to kind of look at these numbers and make sense of them, right? Kind of discuss those for a minute in terms of the slope and the length of certain lines, all right? You're going to remind me to do that. Bye.